Strauss.
Yep.
For number 3, you should have put the answer to the first part of it.
Should I?
Yeah. Because I screwed someone up bad and I can't figure out what it was.
Okay, so let's take a look at. Oh, you need some help. Could you read number 1 for us, Garrett?
Carbon-14 is a radioactive isotope of carbon that has a half-life of 5,730 years. You start with a sample that contains 1,000 C14 atoms. How many C14 atoms will be around in 22,920 years? K is 1.20 times 10 to the negative 4th years.
Okay, so the problem is asking us to find the number of atoms that will be left. Okay? If we're asked to find atoms, this is the equation we're going to use. Okay? N equal to n sub 0 e to the negative kt. Write down everything that you know. So how many atoms, radioactive atoms, did we start with? 1,000. What is the time? So how much time is going to elapse? They said 22,920 years. So what's the deal with that half-life thing? The first sentence says that carbon had a half-life of 5,730 years. That has nothing to do with the problem. It's a distractor. Okay? So all it did was state the half-life of carbon. The time is how much time has elapsed. Yep?
If it ever says the half-life, can we just ignore it? For this?
Yeah, for our class. You can use the half-life to calculate K, but I'm always just going to give you K. Okay, but if you go further on in science, in AP Chem or college, you can use the half-life to calculate K. So we plug in our numbers, 1,000, the exponential, don't forget your negative, 22,920 times 1.20 times 10 to the negative 4th. And if you plug it into your calculator correctly, I believe the answer you get out is 63.5. And you can't have half an atom. So you round it up to the nearest whole number, which would be 64 atoms. So in other words, after 22,920 years pass, 64 carbon atoms will be left. Did they disappear? No, they became nitrogen. Right? That's radioactive carbon-14. Carbon-14 goes through beta decay and becomes nitrogen. Any questions on number 1? All right, then could you read number 2 for us, Emmy?
The beta decay of potassium-40, which is a natural part of the body, makes all human beings slightly radioactive. The most 70 kilogram person alive is 170 grams of potassium in his or her body.
So, like I said yesterday, all of us are about 70 kilograms. That means all of us contain about 170 grams of potassium. Now, how much of that potassium is the radioactive potassium, potassium-40? Well, if you read in Part A, it says that 0.0118% is the radioactive potassium, potassium-40. So how do I do this calculation? Well, you take your amount times your percent. But remember, Matt, you must divide your percent by 100. So if you do this, then you will get that answer. And that is the amount of radioactive potassium in your body, about. So about 0.02 grams of radioactive potassium. Not a lot, but enough to detect with a Geiger counter. Part B, Quinn, asks us to calculate the number of atoms of radioactive potassium-40. So you start with your grams from Part A. divide by 40 because potassium 40 weighs 40. Convert it to moles, moles to atoms, and I get 3.03 times 10 to the 20th atoms. That is the starting point. Okay? That's the amount of radioactive atoms in your body when you are alive. So this many atoms, Stephanie, are in your body right now, radioactive, potassium 40. Okay, letter C. Could you read that one, Jared?
An adult weighing 70 kilograms was found in the Swiss Alps frozen. Using a Geiger counter, the amount of K40 in the frozen body was determined to be 3 times 10 to the 20th atoms. How old are the bones of the deceased person?
Okay, so this actually happened. Someone was hiking and they found a frozen body that had been melted out of a glacier. And then they called some scientists up there, the Italian and French scientists, and they started digging this guy out. Interestingly enough, this guy had an arrow stuck in his back. So, they say that the amount of potassium 40 in the body was 3.00 times 10 to the 20. So, n sub 0 is when you are alive. N is when the object is dead. So this is the final number of atoms, that's the starting number of atoms. We are told that K is 5.415 times 10 to the negative 10th inverse years. And what we are trying to do is find time. How old is the man in the ice? So the equation that we use to solve for this is the ln of n over n sub 0 equal to negative kt. So then let's plug in the numbers. The smaller number, n, should always be on top. N naught goes on the bottom. Then the k constant. When you take the ln of that, I get negative 0.009950. Solve for t. Depending on how many digits you write down, you might get a different answer than what's on the answer sheet. And I get 18 with 3 sig figs, 18 million. Is that right? Yeah. Years old. And the reason why I put a range on there is because, again, depending on what numbers you put in there, your answer might be slightly different. Yes, Rachel?
Do you know what range do you not have to include the range?
You don't need to include the range.
Okay.
I just put it in there so that, like, if you got 21 million, you knew that, okay, I got the right answer. Or if you got 15 million, you know you got the right answer. Just an FYI, I made this problem up, the numbers. No human beings were alive 20 million years ago, okay? The earliest Homo sapiens were about 160,000 years ago. And the earliest humanoids are about 2 million years ago. So, no human being was around 18 million years ago, okay, Sam? So, don't go home telling people that. Okay, number 3. 2 read number 3 for us? Jen?
Radioactive iodine 131 is used in medicine to map the veins and arteries of a human being. K equals 0.0862 days. A doctor wants to determine if Betty's veins are clear, so she gives Betty 100 milliliters of a 3.57 times 10 to the negative 14th molar solution of iodine 131. When the number of radioactive atoms drops below 1.80 times 10 to the 9th atoms, the person is no longer considered to be radioactive. How many days will it take before Betty is not considered radioactive?
Okay, so we're injecting radioactive iodine, and we are giving Betty 100 milliliters of 3.57 times 10 to the negative 14th molar solution. Okay, when the number of atoms drops below 1.8, the person's how many days? So we are trying to find time. What else do we know in this problem? We know the K value. 862 inverse days. We know the final number of atoms. 1.80 times 10 to the 9th atoms. So once you drop below that, when you drop below that value, you are no longer considered radioactive. What is the initial amount of radioactivity Betty received? Well, they don't tell us the number of atoms, but they do tell us, Trevor, how much solution she got. She received 100 milliliters. Now, I want my N naught to be in atoms, but I was given milliliters. So how do I convert milliliters to atoms? Well, the first thing I do, Lauren, is I convert it into liters. Why do I convert it into liters? So that I can use my molarity. The molarity says that in 1 liter of solution, I have 3.57 times 10 to the negative 14th moles of radioactive iodine 131. So I convert my milliliters into liters, my liters into moles using the molarity. And now that I have moles, then my last step is to convert the moles into atoms. And 1 mole is 6.02 times 10 to the 23rd atoms. Three sig figs, 3 sig figs, 3 sig figs. So with 3 sig figs, 2.15 times 10 to the ninth atoms. So that is the starting point. That's the number of radioactive atoms injected into Betty. When it drops below that number, she is no longer considered radioactive. How long will that take? If you're trying to find time, this is the format we will use, just like we did in number 2. Plug in our values. Plug this into my calculator. And I get solve for T. approximately 2.06. And then what's the units on there, Brandon?
Adam, or no, use
What's the K value?
days.
Days. So K's in days, then your times in days. These two always have to match up. Yep, Rachel.
For the, like 10 to the 9th, should it always be the same if you have a problem that's like?
You mean these exponents?
Yeah, should they always be the same?
No. But the top number should always be smaller. And then what should they ask Betty? The bonus question. Oh, come on, some of them know.
I don't know if this is like a trick question or not.
Do you think it's a trick question?
I don't know.
I
Well,
think so.
I have a guess, but
You're a male, so you probably don't know.
well, I have a
You're a female, you walk in, they're gonna take an x-ray of you. What are they gonna ask you?
If you're pregnant.
If you're pregnant or you think you might possibly be pregnant. So any question on number 3 before we go on to the second page? Yep, Lissy. Why don't you do it that way? So you don't make it.
Wait, was this
Yes. So on the first worksheet, we were always using atoms, n's. Okay, but like I said, they really don't do that. The equation you really use are rates. And so numbers 1 and 2 on the next worksheet always used rates. So let's see, who haven't I picked on yet? Matt, could you read number 1?
You have just completed medical school and are working for a walk-in clinic. A patient comes in and complains of pain in the lower abdomen and constipation. One method of examining the inside of the large intestine and colon is through the use of a radioactive barium enema. The initial decay rate of the barium you inject is 13 millicuries. When the decay rate drops below 4 millicuries, the patient is no longer considered radioactive. How many days will it be until the patient is no longer considered radioactive?
Okay, so our equations that we can use in this problem are this one, or we can use this one. It all depends on what you're trying to find. Are we trying to find the rate? Are we trying to find the time? We're trying to find time. It says that how many days will it be until she is no longer radioactive? So, we've got the initial injection of 13 millicurie. When it drops below 4 millicurie, she's no longer radioactive, or he, or whoever that person is. The decay constant is given as 0.05436 days inverse. So that means we're going to use this equation to find time. We plug in the values. Take the ln of that. I solve for t. got 21.7. And suppose I really should have one sig fig here. So I guess the answer should round to 20 days. They wouldn't inject you with that much radioactivity. Usually it's about 2 or 3 days till the radioactivity is gone. So any questions on number 1? Okay, number 2. Did you read that one, Kelly?
Potassium 40 goes through beta decay. About 0.0117% of potassium in the Earth's crust is K40. The decay constant is K equals 5.5011 times 10 to the negative 11th year. While studying rocks in an ancient riverbed, they found a cluster of rocks that have a decay rate of 6.1 decays per hour. All of the other rocks in the air have a decay rate of 3.2 decays per hour. We suspect that the cluster of rocks might not be rocks, but fossilized stromatolites, big mats of ancient bacteria. A living bacterial colony will have a decay rate of 7.82 decays per hour. How old is the fossilized stromatolite?
So you got this ancient riverbed, and there's these rocks in there. And you take your Geiger counter, and you're measuring the radioactivity in all these rocks. And all of these rocks show a decay rate of 3.2, except for a couple of them, which show a higher decay rate. So as a researcher, you have to ask yourself this question. Why would all the rocks have a decay rate of 3.2, but one group of rocks has a higher decay rate? And if you've ever been to Australia, you will see this. Lots of rocks that look like rocks, they're actually fossilized bacteria. And the oldest fossilized bacteria is somewhere around, I think, 1 billion years old. So now how the heck do they figure out that these fossilized bacteria are 1 billion years old? By the way, in case you're wondering what bacteria look like, remember my little jar, Strauss World? Nice big jar of bacteria. Come back in 1 billion years, with enough pressure and time, I can make that turn into rock, or a fossilized bacteria called a stromatolite. Cool stuff. So, we think that this rock right here is not a rock at all, but fossilized bacteria. So that means, is it alive or dead right now? Dead. So that means that's the final rate. Whoops, I wrote this down wrong. That's the wrong number. 6.81. Sorry. So it's dead. That's the decays per hour. Now, what's the decay rate of a living bacterial colony? Well, you get your living bacterial colony out. Get out your Geiger counter and measure the radioactivity of a living bacterial colony. And a living bacterial colony has a decay rate of about 7.82 decays per hour. And tell us the K is 5.5011 times 10 to the negative 11th inverse years. We are trying to find time. So all at about 0.0117%, that's just a distractor, you don't need it. Our equation is ln R over R naught is equal to negative KT. Plug in our numbers. Negative 0.13829. Solve for T. And I get about 3 sig figs, 2.51. About 2.5 billion years old. So that would be old bacteria fossils. So that's how they do this stuff, Brandon. When you're reading a scientific journal and they're like, oh, we found a bone from 1 million years ago. Or we found some bacteria from 300 million years ago. It's through this process. Do you have any questions